Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is electrical safety and Ohm's Law. Our objective today is to apply Ohm's Law to scenarios involving electrical safety. Additionally, we'll discuss safe work practices when performing electrical work. This lecture does not cover circuit protection devices like fuses, breakers, and ground fault current interrupters, nor grounding and bonding. These topics, also related to electrical safety, will be addressed in later lectures. This topic is an extension of the General Industrial Safety lecture, available at the Big Bad Tech channel. If you haven't watched this lecture, by all means do so now. I'll be right here waiting for you when you return. The same caveats I gave during the General Industrial Safety lecture also apply to this one. The topic of electrical safety is far too important to be covered in a single online lecture by an individual that is not even remotely qualified to do so. If you are seeking formal safety training or certification, I recommend you visit your local community college or a reputable and recognized service provider. This lecture's only purpose is to provide general electrical safety guidance and, most importantly, gives a chance to apply Ohm's Law. My intention is that you understand, appreciate, and respect electricity, not fear it. It is as dangerous as it is useful, and there are laws, natural and man-made, that govern its wise use. If you've been following this playlist in its intended sequence, you may be shocked, pardon the pun, to find a lecture on electrical safety appear so late in our discussion. Customarily, this is the first chapter of most textbooks, and presented in such a sequence implies high priority. This is the wrong way to do it. Electrical safety is absolute nonsense without an understanding of Ohm's Law. It is my intention with this series to provide you with a basic, progressively expanding skill set that will allow you to apply previously obtained knowledge to an ever-growing pool of applications. Today we'll use Ohm's Law to understand electrical safety. Obviously, a saltwater-soaked person standing on a metal platform touching a bare high-voltage wire is a recipe for disaster. This is all kinds of dumb, and your newfound appreciation for Ohm's Law tells you so for several compelling reasons. 1. A person is a conductor. Everything is a conductor. It's just that some conductors are better than others. A saltwater-soaked person is an especially good conductor, with extremely low resistance. 2. A metal platform is also a low-resistance conductive path connected to the earth, something we often use as a reference plane for voltage measurement. 3. The wire is high voltage. The magnitude of this voltage is often made with reference to ground, that same plane the worker is standing on. If the worker touches the bare wire, there is a difference across their body, and current will flow through him or her. The magnitude of current via Ohm's Law is directly proportional to voltage and inversely proportional to resistance. If the voltage is high and the resistance is low, the current will be exceptionally high. Let's take this analysis one step further and look at it from the perspective of power and energy. Power is voltage times current. With high voltage and high current, the power transferred to this worker is high. And if energy equals power times time, if the power is high and if the path is sustained for a long time, the energy delivered to the worker is extremely high. Customarily, I've been speaking about energy as if it was a force applied for a distance, because the joule, the SI unit of energy, is in actuality 1 Newton of force applied for 1 meter. However, different forms of energy exist, notably thermal. Depending on your choice of units, joules of energy could be equated to either a BTU or a large calorie, where a BTU of energy is the heat energy necessary to raise the temperature of a pound of water 1 degree Fahrenheit, and a large calorie is the heat energy necessary to raise the temperature of 1 kilogram of water 1 degree Celsius. 1 BTU is equal to about 1,055 joules, and 1 large calorie is equal to about 4,186.8 joules. Water heats non-linearly. There are a bunch of different other considerations, but these are pretty close figures. The point is that electrical energy can be changed into heat energy, and this, among other deleterious effects, is what makes high current flowing through part of your body a situation to be generally avoided. Given an understanding of Ohm's Law and power and energy calculations, what are the steps you need to take to avoid the inadvertent transfer of energy, i.e. a shock, when working on an electrical system? Step 1. Avoid high voltage. If the voltage is high, the current will be high. Here's an even better idea. Avoid voltage altogether. Turn it off. Lock it out, tag it out, and test it. Lockout and tagout procedures, if you recall, were covered in the General Industrial Safety lecture. Verify that all sources of hazardous energy are removed. If you don't have to work on energized equipment, don't. Think smart. If you're installing, maintaining, or troubleshooting a solar array, wait until the sun goes down. Not only is the array not energized, the sun won't be hammering on your head the whole time. This does not mean you don't have to follow proper lockout and tagout procedures, but it does mean you have an extra level of protection when the PV array isn't energized. Step 2. Don't be a low resistance path. An insulator needs to be between you and high voltage sources. Make sure your listed personal protective equipment is dry and passes daily inspection. A common piece of personal protective equipment associated with electrical work are rubber gloves. Rubber has a high resistance. Rubber is an insulator. Step 3. If all else fails, don't get shocked for long. The longer you are a conductive path, the more energy that is transferred to you. It is for this reason systems often incorporate protective mechanisms, such as fuses, breakers, and ground fault current interrupters to limit the length of a high current or fault current events. We'll deal with these circuit protection devices in later lectures. Step 4. Follow the law. This is probably the one and only time I'm not referring to Ohm's law. I'm saying follow the appropriate laws governing safe work practices. There is absolutely no reason for you to ever be exposed to high voltage while you are a path of low resistance for an extended period of time. There are mandatory laws and safe work practices established by governing bodies, specifically OSHA and the NEC, established by the NFPA. If we remember correctly, these organizations were introduced in the General Industrial Safety lecture. Obey the law. Finally, step 0. Meaning before all these other considerations even come into play, know what you're doing. Don't just flip switches and push buttons. You are going to get yourself or someone else killed. I know I make fun of your lab partner a lot, but seriously, they are here for the same reason you are. They want to learn. They're just doing a horrible job at it because they can't show up to lab prepared. A lot of industrial accidents are not caused by careless or reckless people. Sometimes industrial accidents are caused by well-meaning people simply lacking the knowledge to do the job they've been pressured into doing. Don't do things you don't understand. I am more than willing to admit there are things that I can't do or don't understand, like listen or care about people's feelings or any of that other made-up stuff. I just don't do it well, and I am not going to pretend I do. If you're being pressured into doing something you don't understand, don't do it until you're absolutely clear no one is going to get hurt. People's lives might be on the line, and one of those lives might be yours. Here's some general safe work practices you should follow when working with electricity. Never work alone. If your team is working remotely, stay in contact with your operations and maintenance organization. Turn the power off if at all possible. Certain measurements must be made with the power on, but if at all possible, turn it off when connecting instrumentation, then turn it back on to make the measurement. Never modify a circuit with the power running. You could accidentally short circuit critical current controlling elements. Discharge or lock out any electrical storage elements like batteries or capacitors. Even if a system is unplugged, such devices can be energized. Know where the emergency stop button is. Know what it does. Have an exit plan. Have 3 exit plans and know where the fire extinguisher is. Use proper personal protective equipment, including safety glasses. Remove conductive jewelry like rings, and if you've got long hair, tie it up out of the way. Insulate your body. Use tools with insulated handles, and don't become part of a conductive path. If at all possible, work one-handed and maintain clearance by not leaning on other parts of equipment. This ensures a conductive bridge isn't formed through your body. Let's get to the heart of this lecture, but before we do, let's get this one out of the way. There is this saying that it's not the voltage that kills you, I can't even finish it. It's just so stupid. You know what I'm saying. If you don't know what I'm talking about, just let it be. Trust me, you're better off. This saying is stupid because without voltage, charges won't move. This is like saying it's not the gun that kills you, it's the bullet. Listen, you can take a 62 grain M855A1 5.56 millimeter enhanced performance round with a solid copper core and a steel penetrator tip and chuck it at a wall as hard as you possibly can. but after a couple tries, you realize using an M4 carbine might yield better results. The rifle makes the bullet move. Voltage makes current move. The bullet won't move without the rifle. Current won't move without the voltage. Voltage will kill you because high voltage causes high current and low resistive paths. This being said, there are distinct levels of unpleasantness associated with increasing levels of current. To further complicate matters, quite like eating a pepper is distinctly different than getting blasted in the eyes with pepper spray, there are areas of the human body that are notably more vulnerable to current than others. The human heart has this thing in it called the sinoatrial node, or the SA node, which is tissue that generates regular electrical impulses that serves to regulate the pumping action of the heart. It's the pacemaker. If the SA node is taken out or goes into random firing, something called AFib, the heart can't pump, and you guessed it, you die. Long story short, if current has to travel through your body, make sure it doesn't go through your heart, through your brain, or through your genitals, or anything else you use often or really enjoy using if you ever get the chance. As a general rule, don't get electrocuted anywhere. It hurts. It hurts when 2 milliamperes of current is traveling through you. It really hurts at about 8 milliamperes. You're taking some serious damage at 30 milliamperes. You might have difficulty breathing at around 50 milliamperes. Your heart just stops pumping at 150 milliamperes. And at 300 milliamperes, you're burning and not breathing. The magnitudes of these current levels might seem surprising to you, given that using different permutations of our power equation, a 100-watt light bulb draws roughly 833 milliamperes of current when hooked to a 120-volt source, and a common 900-watt toaster draws 7.5 amps of current from the same 120-volt source. Don't these devices draw incredibly high current using our existing scale of undesirable effects? 833 milliamperes is off the screen, hitting the ceiling, and 7.5 amps or 7,500 milliamperes is up in the stratosphere. Yeah, but guess what? You're not a light bulb and you're not a toaster. What's the resistance of a 100-watt light bulb that draws 833 milliamperes when hooked to a 120-volt source? Resistance is equal to voltage divided by current. 120 volts divided by 833 milliamperes yields 144 ohms for the light bulb. The resistance of the toaster is 120 volts divided by 7.5 amps, or 16 ohms. Which begs the question, what's the resistance of the human body? The answer, quite like everything it seems, is it depends. It depends upon the path taken by the current. It could go from arm to foot, head to foot, or any other combination. Not only does it depend upon the path it takes, it also depends upon the nature of the tissue it passes through. The human body, quite like a circle, has two sides, an inside and an outside. I never get tired of that joke. Anyways, all the gooey, bloody, squishy stuff on the inside has pretty low resistance, but it's wrapped in normally high resistance dry skin. Wet or sweaty skin is relatively low resistance. Broken skin is also low resistance. And if being electrocuted wasn't bad enough, with broken skin, now you're bleeding. Here's a resistance reading taken from hand to hand while my skin is dry and unbroken. It's showing 0.714 mega ohms or 714 kiloohms. No, I am not going to stab myself with a pointed probe in the next frame, but I am going to tape a picture of your lab partner to a punching bag and go out in the garage and pummel it for a solid hour before I take another resistance reading. Returning in a far better mood, we found the resistance reading for the same path has dramatically decreased to 9.21 kiloohms, more than 77 times less resistance just because I'm covered in an electrically conductive film. Everyone's body composure is different, and it varies from day to day, so if you observe different values for your own body, don't think you're sick or special. Now, using our previous understanding of Ohm's law, answer the following questions. Pause the lecture and see if you can determine the voltage necessary to produce a mild shock at 2 milliamperes for both dry and wet conditions. Number 2, Determine the voltage necessary to produce a severe shock of 30 milliamperes for both dry and wet conditions. And finally, number 3, what is the current produced if I was to make contact with a 120 volt source for both dry and wet skin conditions? What deleterious effects might I notice? Pause the lecture and take a stab at this. Ohm's law states that voltage is equal to the current times resistance. If a mild shock is considered 2 milliamperes, and my dry skin has a resistance of 714 kiloohms, 2 milliamperes times 714 kiloohms, I would expect to experience a mild shock at approximately 1.43 kilovolts. However, if my skin was wet, my resistance has notably decreased, and 2 milliamperes times 9.21 kiloohms means an 18.42 volt source could give me a mild shock. Now we're asked to find the voltage that would produce a severe shock of 30 milliamperes. And again, Ohm's law states that voltage is equal to current times resistance. 30 milliamperes times dry skin conditions of 714 kiloohms means a 21.42 kilovolt source would give me a severe shock of 30 milliamperes. However, wet skin conditions with notably less resistance, 30 milliamperes times 9.21 kiloohms, means a 276.3 volt source would deliver the same severe shock. Our next set of problems asks us what is the current that would be induced through this path by a 120 volt source for both dry and wet skin conditions. Ohm's law states that current is equal to voltage divided by resistance. 120 volts divided by 714 kiloohms yields a current of approximately 168 microamps. You'll know you got hit, but not enough current to be really dangerous. That same 120 volt source, however, in wet skin conditions, when resistance is notably lower, would yield 120 volts divided by 9.21 kiloohms, would yield approximately 13 milliamperes of current. Kind of right about here on our scale of deleterious effects, between very painful and deadly. This is why electrical safety is such critical concern in areas closely associated with water, like kitchens, bathrooms, and showers. The moral of this example problem, if you're going to die wet and naked, make sure it's not electricity that killed you. In addition to electrocution hazards, there exists danger associated with arc flashes. An arc is exactly like a lightning bolt, and temperatures briefly exceed that of the sun. An arc can burn an inadequately protected worker, and if that wasn't enough, any surrounding material exposed to an arc is vaporized and violently expelled. Arcs can occur during high-voltage switching operations, and such operations are always associated with an increased level of personal protective equipment and safety precautions. Be aware that the different flavors of electricity, DC versus AC, have their own unique safety concerns. DC stands for direct current. It does not change polarity nor direction. A DC shock is often associated with a rapid muscular contraction, meaning that a limb touching an exposed conductor will involuntarily retract and break the connection, sparing further damage. AC, not so much. Since AC stands for alternating current, contact with an exposed AC conductor results in muscular spasms and prolongs the exposure time. If a worker is being electrocuted, do not touch them until you can turn the power off safely. The injured coworker then needs to be tended to by an individual trained in first aid, CPR, AED. An AED, by the way, is a device that kickstarts the SA node back into a regular cyclical firing, ironically enough by using a timed and measured quantity of electrical energy. Again, electricity has the capacity for both life and death. Don't fear it. Understand it and respect it. If there is one takeaway from this lecture, it is that being electrocuted and falling into a vat of genetically modified electric eels will not grant you superpowers. Not only will it kill you, it will hurt like hell the whole time you're dying. Radioactive spider bites? These would totally give you superpowers. Finally, I need to level with you and make one thing clear. I am not an electrician, and you cannot use anything you learn from this lecture or any of the other lectures as professional electrical advice. Follow the rules. Follow the code. It is there for a reason to safeguard people and property from electrical and fire hazards. In conclusion, this short lecture took a look at Ohm's law applied to electrical safety. We discussed electrocution dangers and arc flashes. Additionally, we briefly discuss safe work practices when working with electricity. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.